Let's get right into this explainer on the extreme and frankly, absolutely fascinating world of underwater engineering. When we think about offshore energy, our minds almost always go straight to those massive steel platforms towering above the waves. But an offshore installation is kind of like an iceberg. The vast majority of the real work, the actual structure, is hidden way down beneath the surface. So today we're diving into exactly how humans and machines manage to operate in one of the most unforgiving, high-pressure environments on the planet just to keep these massive subsea systems running.
Because here's the thing. To really understand how the offshore industry even survives, we have to ask a pretty basic question. How on earth do you maintain platforms, pipelines, and foundations at crushing depths? These massive structures don't just sit perfectly on the seabed forever. They're constantly getting battered by wave fatigue, relentless corrosion, and marine biofouling. They need regular checkups, valves need to be manually turned, and the ocean floor, well, it's definitely not a place we humans can just casually stroll into without some serious, heavy-duty support.
And this contrast right here hits the nail on the head. We're looking at a fragile human diver in a wetsuit working in the shallows, compared to a massive, 2-ton titanium robotic vehicle operating deep in the abyss. These are basically the two paths the industry has carved out over the decades for underwater work: human diving and remotely operated vehicles, or ROVs. Each path has its own specific use cases, its own brilliant tech, and, as we'll see, its own very hard limits.
Okay, let's start near the surface. Section 1, air diving. We're looking at the shallows, anywhere from 0 to about 50 meters down.
For these shallower jobs, a diver uses surface-supplied air. Basically, they're tethered by an umbilical. It's this thick composite hose pumping down breathing air, comms, a safety line, and even hot water to keep their suit warm. But there is a very hard biological stop here. See, compressed air contains nitrogen. At sea level, totally harmless. But as you descend, the water pressure actually forces your body to absorb more of that gas. By the time you hit 30 or 40 meters, you start feeling it. And by 60 meters, the nitrogen literally acts like a heavy anesthetic. It causes something called nitrogen narcosis. The diver becomes severely impaired. They are essentially heavily intoxicated. So for safe, routine engineering work, air diving simply cannot take us any deeper.
Which brings us to Section 2, saturation diving. Under pressure, operating from 50 to 300 meters deep.
As we push further down into that twilight zone, the rules completely change. We have to completely engineer our way around the body's deadly decompression problem. Take a look at the sheer scale of a diving support vessel, or DSV. This isn't just a ship, it's a highly sophisticated floating base. Inside the hull, there's a network of pressurized steel chambers called the SAT complex. Divers actually live inside these tubes at the exact pressure of their working depth for up to 28 days at a time. By staying at that extreme pressure, their bodies become completely saturated with dissolved gas. The massive benefit here? They don't have to go through a dangerous hours-long decompression cycle after every single shift.
And guys, the daily commute for these engineers is just wild. Imagine waking up in a pressurized metal tube on a ship's deck. You transfer straight into a specialized capsule called a diving bell. Then, that bell is lowered through a hole in the ship, literally called a moon pool, all the way down to the seabed. You lock out, swim into the freezing, pitch-black water to do heavy manual labor, and then you climb back into the bell and get winched back up to your living quarters. All this happens without your body ever experiencing a change in atmospheric pressure.
Now you might be wondering, how do they breathe down there without getting that toxic nitrogen narcosis we talked about earlier? Well, they breathe a custom gas mix called heliox. They completely strip out the nitrogen and replace it with helium. Helium is inert, so no narcosis. It perfectly bulks out the oxygen for deep breathing. But because helium gas is so incredibly light, it severely distorts the vocal cords. So you have these elite, highly trained professionals executing critical subsea engineering tasks, all while communicating over the radio with high-pitched Donald Duck voices. It's bizarre, but it's absolutely crucial for their survival.
But there is a massive penalty for living like this, and it comes down to the number 1 hour. Because the diver's body is fully saturated with that gas, decompressing them back to normal surface pressure has to happen excruciatingly slowly. If they go too fast, the gas expands into bubbles in the bloodstream, which causes the bends, and that can be fatal. It takes about 1 hour of slow decompression inside the ship for every single meter of depth they worked at. To put that into perspective, a diver coming back from a 180-meter job is going to spend almost an entire week just sitting in a chamber decompressing.
So what happens when we go deeper? Section 3. The rise of ROVs. Welcome to the abyss, 300 meters and beyond.
Once you plunge past that 300-meter mark, the ocean just becomes entirely too hostile for human biology. The pressure is immense, and the decompression time becomes impossible. So we have to rely completely on machines, remotely operated vehicles. And the evolution here is staggering. Early on, inspection ROVs were basically just fragile floating cameras. You drop them in just to look around. But modern, heavy-duty, work-class ROVs, they are multi-ton beasts. They aren't just watching. They are doing the heavy physical labor and active construction on the seabed.
Think of a work-class ROV as a pilot's high-tech underwater avatar. Let's break down its anatomy. It's got multiple ducted thrusters, meaning it can hover and maneuver in full 3D with pinpoint precision. Down there, it's pitch black, so it relies on an array of zoom cameras and sonar to see. But the real magic is in its dual robotic manipulator arms. Usually, one arm grabs the structure to anchor the sub, while the other, highly articulated arm does the fine detail work, like turning actual valves or cutting cables. It even has tooling skids that swap out equipment like torque tools and giant cleaning brushes.
But this robot isn't a completely independent submarine. It's tethered to the surface ship by an umbilical cable. And actually, calling it a cable is a bit of an understatement. It's the robot's central nervous system. This huge composite line constantly pumps down high-voltage electricity, real-time fiber optic video so the surface pilots can see everything in high def, and hydraulic fluid to power those massive robotic arms. It's a literal physical lifeline stretching miles into the deep.
What's really fascinating here is that the entire offshore industry had to redesign itself around these robots, because a metal claw, no matter how advanced, just doesn't have the dexterity of human fingers. So, equipment on the ocean floor had to be reimagined. Valves are now made much larger and are brightly labeled. They use specific connection ports called hot stabs and flying leads. Basically, these are standardized, oversized sockets engineered so an ROV can easily plug in a hydraulic line. It takes a complex manual task and turns it into a plug-and-play operation for a robot.
To really wrap your head around how far this robotics tech has taken us, think about the number 2,800. The deepest subsea well successfully installed right now sits at a mind-bending 2,800 meters down in the Gulf of Mexico. That's over 9,000 feet deep. The pressure there is unthinkable. It's a completely guidelineless, diverless setup. Every single piece of equipment, every connection, every bit of future maintenance, it's all done entirely by remote-controlled machines operating in the freezing, crushing dark.
As our deep-sea infrastructure pushes further and further down, we've clearly crossed the threshold of what human biology can handle. We've gone from a fragile diver relying on compressed air in the shallows to deploying massive titanium avatars thousands of meters into the abyss. It really makes you wonder, as umbilical tethers get better and as AI starts stepping in to help pilots navigate these extreme environments, what exactly are these underwater robots going to build, fix, or discover for us next? Thanks for joining me on this explainer. Keep questioning and keep learning.